Hi, Assalamualaikum. Okay, guys, as usual, don't forget. Also, okay, thank you. Okay, guys, so let's discuss chapter 3, where the topic is electric current and direct current. Okay, so there are 9 subtopics, and starting by 3.1 until 3.9. And for this, let me explain you that we have 2 different main part for this 4 item. First, okay, we are discussing about the electricity. Okay, while for another 5 subtopics, we are discussing about circuit. Okay, so basically we need to understand this part first. What does it mean by current? What is the principle or concept? Okay, explained by the ideas carried out by our researcher before, and then we just apply all the currents to be in the circuit. So there are so many different type of circuit involving the ideas introduced by Mr. Kirchhoff, and then how do we apply it for the potential divider, also for the potential meter. Alright, so we need to go for this part. Okay, I think in about 2 or 3 hours lah. Okay, so try to understand the concept later. Okay, so let's start by the first subtopic. So we need to understand what is current actually. Okay, under electrical conduction, we need to know what is current. So how to explain it? Alright. So basically, you need to describe microscopic model of current. So what is current? So this is the equation. And how do we use the equation of current? And how do you calculate the charge flow through the circuit or wire? Okay. Okay, basically, we just start by the description of microscopic model of current. Okay, what is current? Conductors contain so many free electrons and move randomly. Alright. So when the wire just connected to the terminal of the battery, so that the potential difference between the terminal of the battery sets up an electric field inside the wire and parallel to it, directed from the positive towards the negative terminal. Okay, so normally by connecting a wire, we have applied an electric field. Alright, so the electric field produced there, where it just starts from the positive terminal towards the negative terminal inside the battery. Wire. Okay. So thus free electrons are attracted into the positive terminal, so are forced to differ in one direction. Okay, so remember, electron is a negative charge. It will be attracted towards the positive terminal, isn't it? So it's just against the electric field. Alright, so seems like they are forced to drift in one direction, which is towards the positive terminal. Alright, this direction is in the direction opposite to the electric field. See again, because the electric field starts from the positive terminal towards the negative terminal, but the electron just attracted towards the positive terminal, so it's just against the direction of electric field. So the velocity of this free electron is called drift velocity. Okay, basically, as we know, the electron just move in random direction, but at the same time, okay, let's say this is the battery. So this is our positive terminal. So this part become positive lah, according to the battery terminal. Alright, which is positive, and the other side is negative side. So this side become as negative part. Okay, because it just connected to our negative terminal of the battery. So as we know, according to the situation, the electric field produced must be directed to the left, isn't it? Starting from positive towards negative. So this is the electric field direction. Okay, that one is our E. So as we know, electron is a negative charge, so it will be attracted towards the positive terminal. So this is the electron, so the electron will be attracted towards the positive terminal. Alright, so basically, as I told you before, the electron just move in random direction, so it will drift little bit towards the positive terminal. So parallel to E, the distance here, that one is our drift displacement, isn't it? So giving you drift velocity. So the electron drift a little bit here. So the displacement, which is parallel to the electric field now, giving you our drift velocity. So what is drift velocity? So the drift velocity of the free electrons is the mean velocity of the electrons parallel to the direction of the electric field when a potential difference applied. Okay, so remember, the drift velocity exists when the potential difference applied. Why? Because we have produced an electric field. So by having an electric field, then the electron attracted towards the positive terminal. So seems like the electron just drift a little bit there, producing our drift velocity. Okay, all right. And then for the next part, okay, what is current? So current I is the rate at which charge move through an area A, such as the cross section of wire. So this is the cross sectional of wire, then the current just passes through it. Okay, conventional current is defined to move in the direction of the electric field. Okay, before this, we just assume that the current just be like this, and we are talking about the flow of positive charge. But now, according to the latest one, okay, we are talking about the flow of current, where the carriers now is an electron, which is negative. So it must be in opposite direction of current actually. Okay, so based on that, positive charge move in the direction of the electric field and the same direction as the conventional current. See, for this, let's say this is the direction of electric field, which is directed to the right. So when the when the carrier charge is a positive charge, seems like the flow of charges also to the right, isn't it? So its direction still the same with the direction of electric field. That one is under conventional current. But according to the our latest research paper now, okay, we are talking about a negative carrier charge. Okay, so negative charges now move in the direction opposite to the electric field. For this, let's say the current is just flow to the right. At the same time, the electron just move to the left. Okay, flow to the left here. So it seems like the direction of current actually opposite to the direction of E. Okay, so suppose current just directed to the the flow of electron just directed to the left. So it just opposes the direction of current and for conventional current. Okay, so now remember, for our syllabus, we are talking about a current flow where the carrier charge now is an electron. So normally the flow of electron must be opposite to the direction of current. Okay, for example, for this. Okay, so this is our cell, the positive terminal and negative terminal connected to a bulb, all right, and then connected to the negative terminal. So according to this situation, it seems like the current starts from positive terminal through the wire and then reach the negative terminal, isn't it? Seems like the current flow just in clockwise direction. But based on our researcher now, it seems like the flow of current actually represented the flow of electron. So electron is a negative charge. It just starts from the negative terminal, attracted towards the positive terminal. So it seems like the flow of electron just in opposite direction of current. When the current just flow in clockwise direction, so that the electron just flows in anti-clockwise. Okay, so this is the explanation. The direction of current flow from the positive terminal to the negative terminal one was decided before it was realized that electrons are negatively charged. Therefore, current flows around a circuit in the direction of a positive charge would move, electron move the other way. Okay, however, this is not method in, okay, but it's okay lah. Alright, so actually remember the ideas of current before, okay, seems like it just start from positive terminal towards the negative terminal. But by talking about the flow of electron, where the electron is our carrier charge, it must be in opposite direction of current and conventional current before. Alright, okay, so what do we have now? Okay, how to define the electric current? So electric current is defined as the amount of charge that passes through the wire's full cross-section at any point per unit time. Okay, or we may simplify it to be like this lah. So current now representing the number of charges per unit time and the charges through the area lah. Okay, so the steady current is defined as I equal to Q over T. So this is for any steady current. For this, we are talking about changes in Q, also in time, isn't it? Okay, but for the steady current, we take it as I equals to Q over T. All right. The unit of current is ampere, capital A. Okay, or how to spell it, ampere. All right. So how do we use the equation of current? Okay, before that, what is Q? Q is the charge, isn't it? So the total charge equals to NE, where E is the magnitude of charges and N is the number of charges. Okay, for example, by giving you a wire carries a current of 1.5 amperes. So they ask you how much charge flows through a point in the wire in 5 seconds and how many electrons cross a given area of the wire in 1 second. Okay, so based on that, what do we have? I, and then time, also time. Okay, first, by giving you a current, they ask you to find the the magnitude of charges, okay, in 5 seconds. So I equals to Q over T, Q equals to IT, I given already, also the time also given here, then you will get the total charge. Okay, and how many electrons? They ask you to find the number of electrons. Okay, so Q equals NE. Okay, and at the same time, dQ equal to I dt. Alright, from this equation, Q equals to Q. Okay, so N equals to dQ over E, where dQ equals to I dt. Alright, so you just substitute the current, and then the time given is 1 second, and the charge, the magnitude of electron is 1.6 exponent negative 19, so that you will get the number of electrons. Okay, so this is the way how do we use the equation. Okay, and then for the second subtopic, we are discussing about the Ohms law and resistivity. So what is the ideas introduced by Mr. Ohms before, and how do we relate it with the resistivity? Okay, so in this subtopic, you need to know how to state and use the Ohms law, how to define and use the resistivity equation, which is rho equal to RA over L. So rho here representing the resistivity. Okay, it's not density, resistivity for this chapter. And then how do we sketch a graph of V against I for the Ohms law? Okay, all right, so what is the ideas introduced by Mr. Ohms before? Okay, we call it as Ohms law. So Ohms law states that the potential difference across a conductor V is directly proportional to the current I through it if its physical condition and the temperature are constant. So V and I, they are directly proportional, but the condition is at constant temperature. Why? Because at constant temperature, the resistance also constant, isn't it? So that V and I, they are directly proportional. Okay, so based on that, V over I equals to constant because V and I, they are directly proportional, isn't it? So the constant here just equals to R. So this is the Ohms law where V equals to IR. Okay, so R is the constant. So remember, V and I, they are directly proportional but at constant resistance. So how do you get constant resistance? At constant temperature, isn't it? Okay, so now what is the resistance now offered by a conductor depends on the following factors. Okay, now resistance depends on length, cross-sectional area of the conductor, nature of material, and temperature of conductor. Okay, how do you get that? From the equation later. Let me show you. The equation of resistivity. Okay, I'll leave it first lah. Okay, so remember, now resistance depends on these 4 factors. First, length. Okay, longer wire giving you higher resistance. Okay, and then for the cross-sectional area, larger cross-sectional area giving you smaller resistance. Okay, And then nature, it depends on the type of material lah. Different material giving you different resistance. Okay, and the temperature of conductor, of course, at higher temperature the resistance also higher, isn't it? Okay, so this is an example given lah. Two different wires with a greater cross-sectional area compared to this, and then shorter than this. Okay, so by having this, what happened? Shorter giving you lower resistance, larger area giving you lower resistance. Okay, and then for this, longer wire giving you higher resistance, smaller cross-sectional area also giving you larger resistance, isn't it? Okay, so how do we get that from the equation of resistivity actually? Okay, so now we just define and use the resistivity. Okay, the symbol is rho. So resistivity is a measure of a material's ability to oppose the flow of electric current through the material. Okay, resistivity now is defined as the resistance of a sample of the material of cross-sectional area of 1 meter squared and of length 1 meter. So it is constant, values depends on the type of material. So normally for the same materials, the resistivity is still the same. Okay, so by giving you two different type of materials, so that the resistivity also different lah. Okay, alright, so the equation of resistivity is Ra over L. So resistivity depends on Ra also L. Okay, so what is R? Resistance. A is the cross-sectional area of the wire and L is the length of the wire, and the unit of resistivity is ohm meter. Okay, so by arrange the equation here, you will get R equals to rho L over A. Okay, so this is the way how do we explain these four factors before. Okay, R depends on length. Okay, also the cross-sectional area. Okay, but remember R and L, they are directly proportional. Longer wire giving you higher resistance, and R and A, they are inversely proportional. So greater cross-sectional area giving you lower resistance. Okay, so this is the explanation based on this. Okay, the resistance of a wire, like the resistance to flow of water through a pipe, depends on the size and geometry of the wire. See, larger cross-sectional area, easy for water to flow, isn't it? So the resistance is lower. Longer wire, okay, present more resistance, because seems like water is quite hard to flow through a longer pipe, isn't it? So this is the example and how do we explain the current flow and the resistance of current flow. Okay, next, the material from which a wire is made, it also affects its resistance, and current flows easily through conductors and only with difficulty through insulators. So different type of material giving you different resistance. Why? Because some of the material is under conductors, some of the material is under insulators. So it's quite difficult for the current to flow through the insulator, isn't it? Alright, so the quantitative measure of a material's opposition to the flow of current is called resistivity. Okay, the measurement, the opposition of current flow, we call it as resistivity. So resistivity depends only on the chemical composition of the material, is not shape or size. So remember, resistance depends on the shape of the material, but resistivity just depends on the type of material. Okay, for example, for this, by giving you a copper, aluminum and iron, also silicon, wood and rubber, so this is the resistivity of the material. Okay, but remember, this one for any constant temperature lah. Okay, all conductors have smaller resistivity. Of course, Because conductors is a good metal, isn't it, to conduct a current flow. So the resistance should be smaller, then the resistivity also smaller. But for any insulator, it will have larger resistivity. Why? Because it's very hard for the current to flow any insulator. Okay. Alright, so according to the Ohms law, this is the graph. So we need to know how to sketch a graph of V against I, potential against current. Okay, so according to the ideas introduced by Mr. Ohms before, V and I, they are inversely proportional, where V equals to I, R, isn't it? So that V over I giving you R, which is our constant. Alright, so from that, V against I graph just be like this, where R just a constant. So how to get R? From the gradient. By calculating the gradient, you will get R for V against I graph. So this is for any ohmic conductor. What does it mean? It just obey the Ohm's law. Okay, and then for non-ohmic conductors, okay, the graph just be like this. It's not really on a straight line graph, but it just in curve. Why? Because it doesn't obey the Ohm's law. Okay, the best example given now is a junction diode lah. Okay, what does it mean? V and I, they are not directly proportional. See, V just increase rapidly when the current just increase. See, that's why we got curve here. But for this, V and I, they are directly proportional. By increasing I, V also increase. Again, I increase, V also increase at the same rate. That's why the graph just under a straight line graph. But for the non-ohmic material, the graph just in curve. Means that V and I, they are not directly proportional. Okay? Alright, so I think some example given here, you may try to answer the example for this. For example, in example 3.2, what voltage will be measured across a 1000 ohm resistor in a circuit if we determine that there is a circuit of 2.50 milliamperes flowing through it? Okay, so by giving you the resistance, also the current, they ask you to find the voltage. So V equals to IR. I given already, but in milli, make sure that we need to cover it to be in milli, okay, which is 10 to the 1 -3, the prefix, alright, and then multiplied by 1000, giving you 2.5 volt. Okay, another example is example 3.3. Okay, by giving you a wire where the length is 2 meters and its diameter is 1 millimeter, has a resistance of 0.45 ohms. What is the resistivity of the material used to make the wire? Okay, so by giving you the length of wire, the diameter, check the unit, it's just in millimeter. We need to convert it to be in meter, okay, in calculation. And this is the resistance R. So what is the resistivity? They ask you to find rho. Okay, so rho equals to RA over L, where A is the cross-sectional area, which is pi R squared, where R equals to D over 2, so that you will get this. So we just substitute the diameter given here, but remember in millimeter should be 10 to the power -3, then you will get the cross-sectional area in meter squared. Substitute into the equation of resistivity here, R given already, so this is the area calculated just now. And then this is the length of the wire, which is 2 meters, so that you will get the resistivity. Alright, okay, and then for 3.3 subtopic 3.3, we are discussing about the variation of resistance with temperature. So remember, so normally by changing the temperature, the resistance also change. So how do we explain it? Based on the effect of temperature. And what is the equation? So this is the equation lah. Okay. Alright, so alpha is a constant, but normally the constant given now just at temperature, normal temperature, which is at 20 degree Celsius. Okay, how to explain the effect of temperature? Alright, so now let's discuss about the metal. The resistance of a metal or conductor depends on, okay, as we know, it depends on nature of material, which is resistivity. What do I mean? It depends on the type of material. Different type of material, different material giving you different resistivity. And then the resistance also depends on the size, okay, which is length, also the cross-sectional area. Okay, and then resistance also depends on temperature. So by having different temperature, so that the resistance also different. So based on this equation, R equals to R naught 1 plus alpha delta T. So delta T equals to T final minus T initial. All right. So this is the initial temperature, and this is our initial resistance at T naught lah. And this is the new temperature, so that this is the new resistance at the new temperature, where alpha just a constant. Okay, so the resistance of metal increases with increasing temperature. So at increasing temperature, R also increase. So as temperature increases, the ions of the conductor vibrates with greater amplitude. More collision occurs between free electrons and ions. So these electrons are slowed down, thus increases the resistance. So this is the way how do we explain it. Okay, so by increasing the temperature, we have increased the vibration of ions and electron inside the metal. So what happened? The collision, number of collision just increase, so that it just slow down the movement of electron there, so that the resistance increase. Okay, how do you use the equation? Okay, so the equation given now is R equals to R naught 1 plus alpha delta T. So based on this, by rearrange the equation, you will get alpha equals to delta R over R naught divided by delta T. And by rearrange the equation, so what is delta R? Delta R equals to R minus R naught. Okay, so you may get this from this lah. Alright. So the resistance of a metal can be represented by the equation below. Okay, R equal to R naught 1 plus alpha delta T. Alright, so R minus R naught giving you delta R, as I told you before. So by rearrange the equation and by substituting the equation given here into this equation, you will get this, where delta R equal to R naught alpha delta T. So that giving you this equation. Okay, I need to show this. Okay lah, how to get that? From this, you will get R equals to R naught plus R naught alpha delta T. Transfer R naught to the other side, giving you R minus R naught equals to R naught alpha delta T. So this is delta R equals to R naught alpha delta T. So this is the question given just now. Okay. Alright, so how do you use the equation? Okay, please refer to example 3.4. Under this example, a platinum wire has a resistance of 0.5 ohms at 0 degrees Celsius. It is placed in a water bath where its resistance rises to a final value of 0.60 ohms. Okay, what is the temperature of the bath? Okay, now, so by giving you, this is R naught and T naught. Okay, this is R naught and this is T naught. So where the resistance rises to final, okay, this is the new R. So they ask you to find the new temperature. Okay, how is it? Okay, alpha given already. So based on this, by using the equation given before, the equation here, so by rearrange the equation, you will get delta T equal to delta R over alpha R naught. Delta R equal to R minus R naught. Okay, substitute R and R naught. Alpha given already, also R naught again, so that you will get delta T, where delta T equals to T naught plus delta T equals to T minus T naught. Isn't it? So by rearrange the equation, you will get final temperature equals to T naught plus delta T. Okay, T naught given already, which is 0 degrees Celsius, and delta T given getting now is 51 degrees Celsius. Plus it and you will get the final temperature. Okay, or example 3.5. A narrow rod of pure iron has a resistance of 0.10 ohms at 20 degrees Celsius. What is its resistance at 50 degrees Celsius? Again, okay, this is R naught and T naught, and this is the new temperature T. Alpha given already, so they ask you to find the new resistance R lah. Okay, so R not given, T not also given here, and then this is the new temperature T. By using this equation, substitute all the values, and then you will get the new R, which is at the new temperature. Okay. And then for the last example, example 3.6. Okay, by giving you two wires, which is P and Q with circular cross-sectional area. Okay, so we know that for any cross-sectional area which is in circular shape, okay, the equation is pi r squared or pi d squared over 4. Okay, so two wires given out P and Q made of the same metal. Okay, what is the hidden info? Same metal, rho should be the same, and have equal length. So length also the same. Don't forget rho equal to each other, also length. So if the resistance of wire P is 3 times greater than wire Q, RP is 3 times than RQ. Determine the ratio of their diameters. So they ask you to find the ratio between P and Q, which is in diameters, and dP over dQ. Alright, so what do we have now? First, rho P, rho Q equal to each other, we take it as rho only. And then the length of wire P and Q also equal to each other, we take it as L. Alright, so from the equation of resistance equals to resistivity L over A, where A equals to pi d squared over 4, because the shape of the cross-section area given are just in circular shape, isn't it? Okay, and then RP is triple than RQ. Okay, so from this we just start the calculation. RP equals to 3RQ, where RP is rho L over A of P, and RQ equals to rho L over A of Q. Okay, but remember, rho P and rho Q equals to each other, we take it as rho only. LP and LQ also equal to each other, we take it as L only, so that you will get this. Rho and rho cancelling each other, also L and L cancelling each other, also pi and pi here. Okay, so that by simplify the calculation here, you will get the ratio of dQ and dP equals to square root of 3, or the ratio of dP and dQ giving you 1 over square root of 3. So this is the way. Okay, because according to the question, they ask you to calculate the ratio of the diameters. Okay, so it can be Q to P or P to Q, doesn't matter. Okay, so you may get two different answers here lah, but still correct. Okay. Okay, so for the next subtopic is electromotive force, internal resistance, and potential difference. Okay, so according to this subtopic, students should be able to define EMF and internal resistance of a battery, state the factors that influence the internal resistance, describe the relationship between EMF of a battery and potential difference across the battery terminals, and use the terminal voltage. Alright, so the main problem faced by students here normally in differentiate between EMF and terminal voltage. So what is that actually? How to differentiate these two things? Okay. Alright, so let's start by the first part, which is the definition of EMF. Okay, and the internal resistance of a battery. So what is EMF actually? So there are so many different definition of EMF. Okay, first, EMF, okay, representing the electromotive force. Okay, what is that? Defined as the electrical energy that generated by a battery so that the charges can flow from one terminal to another terminal of the battery through any resistor. Okay, seems like here we need to transfer an electron from one terminal to another terminal, isn't it? So the energy needed here. So the energy provided by the cell or the battery, we call it as EMF. Okay, to transfer the electron from one terminal to another terminal through a resistor. Okay, that one, energy provided by the battery, we call it as EMF. Or EMF of a battery is the work done per unit charge. Again, work done per unit charge. So to transfer the charge, okay, the work done here, or the work provided by the battery. Okay, and then the EMF of a battery is the potential difference across the terminal of the source in the open circuit where the current equals to 0. Okay, what does it mean by that? Okay, let me explain later. Say for this open circuit means that the circuit is not complete, or the switch is off, or the current doesn't flow through the circuit. Okay, this is the meaning of open circuit. Don't be confused. Open circuit means that the switch is off or the current doesn't flow through the circuit, and the unit is volts. Okay, so for any closed circuit, just be like this, the current just flow through the circuit. Open circuit means that the circuit is not complete, okay, or the switch is off actually. Okay, this is switch on and this is switch off. Closed circuit, switch on. Open circuit, switch off. Don't be confused. Okay, for this incomplete circuit, so it's not functioning. No battery also is not functioning. But for this the complete, the circuit is complete, so the circuit is functioning already. Okay, all right. So EMF and internal resistance. Okay, what is that actually? The source that maintains the current in a closed circuit is called a source of EMF. Normally a battery lah. Provide the current, provide the energy, and that one is EMF or battery. Any device that increase the potential energy of charges circulating in circuits are sources of EMF. Okay, again, the battery lah normally a cell. So any device giving potential or energy, and for the charge to complete the circuit, that one is EMF, source of EMF, normally the battery lah. And then a real battery has some internal resistance. Of course, inside the battery there must be a resistance, but the resistance is quite small. We call it as internal resistance, normally called by the chemical things lah, and which is cation and anion, giving some collision with the electron, giving resistance, isn't it? We call it as internal resistance. Therefore, the terminal voltage is not necessarily equal to the EMF. Okay, by having any internal resistance, normally the terminal voltage is not equals to the EMF, should be lesser than. Okay, why? Okay, listen carefully for the explanation. Okay, so let's say there's a battery and connected to a resistor. So we may sketch a simple diagram to be like this. So this thing representing our battery. So remember, inside the battery there must be an internal resistance. The symbol is small r lah. And this is our external resistor. So the symbol is capital R, representing resistance of external resistor. Okay. Alright. So what happened now? Okay, this is the battery. So we call it as EMF, isn't it? Because the energy supplied by the battery. So this is our EMF, and this is our external resistor. Inside the battery we have the internal resistor. Okay, giving you internal resistance lah. Okay, based on this, what is the difference between the EMF and terminal voltage? Okay guys, so let's say there is a cell. This is a cell, okay, connected to an external resistor, and then the switch still off. Okay, and then we just connect a voltmeter through a cell, also through the external resistor. Okay, seems like the switch still open or off means that there is no current flow, isn't it? When there is no current flow means that there is no potential drop by R here, because as we know, V equals to IR, isn't it? So in this case, the current equals to 0. It doesn't flow through the circuit, means that I equal to 0. When I0 giving you 0 V, isn't it? So V drop by the resistor equals to 0. And V drop means that V across the resistor equals to 0. Okay, also for the internal resistance here, and seems like there is no current flow, then the potential drop by the internal resistance also equals to 0. So what do we have now? The reading shown by this voltmeter equals to EMF, while the reading on the voltmeter here equals to 0. Means that on that time, we just measured the EMF. The reading shown by the voltmeter now representing the EMF when the switch is off. Okay, listen, this is EMF. Okay, now by turning on the switch S here, and by turning on the switch, what happened? The current starts to flow, isn't it? The current starts to flow in this direction. So this is the current. I, and I. Okay, again I. So remember, V equals to IR. So in this case, the current just passed through the resistor, so there must be a potential drop by the resistor, isn't it? Which is V equal to IR. So now the potential drop already by R. Also for the internal resistance, the current just passed through the battery here, so it just passed through the internal resistance, so that there must be a potential drop. So that one is VR lah, V small r, and here also V capital R lah, the potential drop by the resistor and internal resistor, isn't it? Okay, so in this case now, please refer to the first voltmeter. The reading on the voltmeter now representing, okay, this is the potential supply, which is EMF, and there must be a potential drop, isn't it? So the reading now on the voltmeter is V equals to EMF minus IR, and the potential drop by the internal resistance, which is EMF minus VR. Am I correct? The reading now, How about for the second voltmeter here? The reading shown by the second voltmeter now is VR, isn't it? So VR equals to IR. The reading on the voltmeter now. Okay, so this is the terminal voltage. Okay, so this V now actually representing the terminal voltage, VT, V terminal. Or here still same as VT. So what is V terminal actually? V terminal is the potential drop by the external resistor, or actually the balance potential supply. And because this is the potential supplied by the cell and already used little bit by the internal resistance, that one is the potential drop, isn't it? Supply and drop. So the net potential supplied now is V terminal. And then what happened to this V terminal? Drop by the external resistor. So actually this is V terminal. V terminal is the potential across the external resistor, or the potential drop by the external resistor, which is balance and potential supplied by the cell actually. It's quite simple. Let's say the EMF supplied now is 10. The potential drop here is 1. 10 minus 1 giving you 9, isn't it? So what happened to this 9 volt? Drop by the external potential. That one is 9. See? 9 drop, 1 also drop. 9 plus 1 giving you 10, which is the supplied one. So this is the difference between V terminal and EMF. Okay, EMF is the potential measured by the voltmeter when the switch is off. There is no current flow, so no potential drop by the internal resistor here, also by the external resistor. So the readout is really EMF. Okay, when the switch is off, by turning on the switch, the current starts to flow, then the potential drop by the internal resistor, also the external one. So the potential drop by the external resistor now representing our V terminal, which is the balance potential supplied by the cell here. Okay, so that is the difference between V terminal and EMF. Okay, so remember, for this situation, by connecting a voltmeter, then the reading getting out is EMF, because there is this one connected to a resistor already. It's not EMF lah. Okay, for the EMF should be when the switch just turn off, to be like this. Then we just connect to the voltmeter. Wait, we just connect this to the voltmeter. The reading now representing the EMF of the cell. Okay, By turning on the switch now, okay, seems like the reading on the voltmeter now representing our V terminal. This one representing V terminal, and because the current flow through the bulb already, inside the bulb we have a resistance, okay, so the potential drop here, so the reading on the voltmeter now representing the voltage across the bulb here, and also that one is V terminal, okay, because some of the potential already dropped by the internal resistance here. Okay guys, so you need to know how to differentiate the difference between the EMF, also the terminal voltage. Okay, I think enough for until this part. I think we just continue later by the next part. Okay, alright. Before that, okay, I think everything given already here. You may read through the notes. Okay, what factor do we have that influence the internal resistance? Alright, so before that, the symbol of resistor just be like this, and then the straight line now representing a wire. Okay, so normally for any wire, I think the resistance is too small, so we may ignore it lah. But for this symbol, the resistance cannot be ignored lah, because I think the value is not too small, including the internal resistance. Okay, but the internal resistance should be smaller than the external resistance normally. Alright, okay, and then what factor just influence the internal resistance? Okay, first, the surface area of the electrode, of course, because a larger area now giving you less internal resistance, and then also the distance between electrodes, where more the distance between the electrodes give you greater internal resistance. It's quite hard for the electron to flow. Okay, and then the other one is nature and concentration of the electrolyte. Okay, less electrolyte, less ionic the electrolyte, or higher the concentration. For any higher concentration of the electrolyte, the internal resistance also greater or higher lah. Okay, and then lastly the temperature. Higher temperature giving giving you less internal resistance. Okay, and then describe the relationship between EMF of a battery and the potential difference across the battery terminals. Okay, as I told you before, remember, EMF minus the potential drop by the internal resistance now giving you the terminal voltage, isn't it? Okay, so when the terminal voltage is smaller than EMF, okay, the battery of EMF is connected to the external circuit with resistance R, of course lah, because this resistance now giving you the potential drop by the external resistance, which is our terminal voltage, isn't it? So the terminal voltage normally smaller than EMF. Okay, and then terminal voltage greater than EMF. Okay, this thing happen when the battery just connected to another battery lah. We are talking about the charging process of the EMF. Okay, so on that time the terminal voltage is greater than EMF, because we need to charge the battery, isn't it? Okay, and then V terminal equals to EMF when the battery of EMF has no internal resistance. Of course, when there is no internal resistance, so that there is no potential drop by the internal resistance, so that the EMF and terminal voltage, they are equal to each other. Okay, alright, so I think you may refer to these two examples. Okay, how to use the equation. Okay, I think enough until this part, because for the next part, I think we need to go further with the series and parallel arrangement of resistor. It's quite interesting, so many hidden info here. They are so tricky. Okay, and then we just go for the kickoff rules. Okay, alright, see you again, bye.